Welcome back everyone, Houston Math Prep here with our examples video for the variation of parameters method in solving second order non-homogeneous linear equations with constant coefficients for differential equations. In this video we're going to work the three examples that we have pictured here, so you can skip to a particular one if you'd like, or just follow along as we go. For the first one here, y double prime minus y equals x over e to the x. So remember, the first thing that we do is we solve the associated homogeneous equation. So we'll be solving y double prime minus y is equal to 0. If we look at the characteristic polynomial for this left side here, that would be m squared minus 1 is equal to 0. You can either add 1 to the other side and then square root, or you can factor this, but we end up getting solutions of positive and negative 1 when we solve this equation. So if m is plus or minus 1, then that tells me that the complementary function is going to be c1 e to the x plus c2 e to the negative x, based on 1 and negative 1 for m. Remember, in the variation of parameters method, we will be finding yp, and that's going to be u1 y1 plus u2 y2. And if you've already solved the associated homogeneous equation, which we have, then we already have y1, which is e to the x, and we already have y2, which is e to the negative x. So both of these are taken care of. We just need to solve our u1 and u2. We'll need 3 Wronskians to do it, so we'll go ahead and find our first Wronskian, which is just simply the first row having our y1 and y2, so e to the x and e to the negative x. The derivatives of these functions in the second row, so we'll have e to the x here as well, and then the derivative of e to the negative x will actually be negative e to the negative x. If we go ahead and do our 2 by 2 determinant, multiplying and subtracting our diagonals, our first diagonal, e to the x times negative e to the negative x, that would give us negative, and if we add the exponents, it would be e to the 0, which is 1, so we get negative 1 for the diagonal here, minus what we get on the other diagonal. Here we have e to the x times e to the negative x. We would get e to the 0 if we multiply those, so that's going to give us 1, and we actually get negative 2 for this first Wronskian. If we now calculate W1, remember W1 is also a 2 by 2 Wronskian with this first column being replaced by 0 and our g of x on the right side, so we'll have 0 and x over e to the x. Our second column, remember, will stay the same for W1, so we'll have e to the negative x and negative e to the negative x. We go ahead and multiply the diagonals. 0 times this exponential down here would be 0, minus what we get when we multiply here. This e to the negative x would put another e to the x on the bottom there, so we would actually get x over e to the 2x. We might prefer to go ahead and call this negative x e to the negative 2x, possibly. Let's go ahead and get our W2, so instead of replacing the first column with 0 and our g of x, we'll replace the second column. So keep your original first column. We'll keep our e to the x and e to the x this time. Now our second column is what becomes the 0 and the right-hand side, x over e to the x. The determinant of this, if we take the first diagonal here, this e to the x will reduce the e to the x on the bottom there, so we'll just get x from that diagonal. And then obviously this diagonal is going to give us 0, so we'll have minus 0, and we'll just end up with x there. And now remember that these Wronskians help us get the derivatives of u1 and u2. So u1 prime, remember, is going to be w1 divided by w. In this case, if we have this x e to the negative 2x divided by negative 2, that will actually be positive 1/2 x e to the negative 2x. And our u2 prime, the derivative of u2, is going to be w2 divided by w. So in this case, we'll get x over negative 2, or negative 1/2 x. Remember, the goal now is to be getting u1 and u2, so u1 is going to be the antiderivative of 1/2 x e to the negative 2x dx. And u2 is going to be the antiderivative of negative 1/2 x dx. This u2, I think, is an easy integral to do here. This is not so bad, right? We just need to do this by parts. We'll go ahead and give you our substitution here. So if we let u, you can bump the 1/2 out if you want. We'll just go ahead and leave it in there. So if u is 1/2 x, and dv in this case is e to the negative 2x dx, then that means du would just be 1/2 dx, and v would be negative 1/2 e to the negative 2x. And so our uv minus integral v du is going to be negative 1/4 x e to the negative 2x. Minus integral v du, I have a negative there also, so that'll make that a plus. We have a 1/2 and a 1/2, so we'll say 1/4, I suppose, out there as well. E to the negative 2x dx. Do that integral there at the end. We'll get negative 1/4 x e to the negative 2x, and then we'll get the reciprocal of negative 2 comes out, so we'll actually get minus 1/8 e to the negative 2x. Remember, we'll leave off our constants of integration when we're finding u1 and u2. Or u2, this should be easy here. This is just a power rule, right? So we get the power goes up by 1, and we divide by the new power, so we get negative 1/4 x squared, leaving off the constant of integration there as well. So we've got u1 and u2. Now remember, our y sub p is u1 y1 plus u2 y2. Now if you get to this point and you forget what your y1 and y2 are, remember you can always just go back to your complementary function. Here our y1 was e to the x, our y2 was e to the negative x. We'll give ourselves a little bit more room here to write y sub p. So y sub p is going to equal all of this u1, negative 1/4 x e to the negative 2x, minus 1/8 e to the negative 2x. All of that times our y1, which is e to the x, so that's our u1 y1 part, plus u2 y2, so plus, here we have negative 1/4 x squared as our u2, and remember our y2 was e to the negative x. And now let's go ahead and attempt to write our general solution here. So remember, y is going to equal y sub c plus y sub p. And our yc, remember, was c1 e to the x plus c2 e to the negative x. Our yp here, so we're going to be multiplying these exponentials into this. So we're going to get negative 1/4 x e to the, if we raise the power by an x here, that would be e to the negative x there, minus 1/8 e to the same thing here, add these exponents, we'll get negative x. And then if we just multiply this, we'll get minus 1/4 x squared e to the negative x. And when you get to this point, you want to look through and make sure that everything seems linearly independent. And we have an issue here. Notice we have a multiple of e to the x. Nothing else is a multiple of e to the x. Here we have a multiple of e to the negative x. This term is not a multiple of the c2 term because we have an x here, and this last term is not a multiple of the c2 term because we have an x squared term here. But this minus 1/8 e to the negative x is actually just a like term with c2 e to the negative x. This is some amount of e to the negative x minus some more e to the negative x, right? So what is some number, some random number, some constant minus 1/8? If we try to put these together, well, it's just going to be some constant, right? So really this term gets absorbed into this term because this is just saying we have some multiples of e to the negative x. So really, to say this the correct way that we want to say it, we just want to say c1 e to the x plus c2 e to the negative x and leave off this term. It's been absorbed into that term, minus 1/4 x e to the negative x, minus 1/4 also x squared e to the negative x. Looking at our next example, y double prime minus 2y prime plus y is equal e to the x times ln x. We'll first solve our associated homogeneous equation, y double prime minus 2y prime plus y is equal to 0. If we look at the characteristic polynomial for this left side, we'll get m squared minus 2m plus 1 is equal to 0. This actually factors into the same thing twice. We'll get m minus 1 quantity squared equal to 0. So we're actually only going to get one solution for m. This is going to have multiplicity 2, so this is what we hopefully remember as a repeated real root. So that tells us that our complementary function will actually be c1 e to the x plus c2. Remember, we need to multiply the other one by x, x e to the x. That's our complementary function. So here we have our y1 is again e to the x, but now this time our y2 is x e to the x. Let's go ahead and find our Wronskians. So our w here is going to be the 2 by 2 determinant with e to the x and x e to the x in the first row. The derivative of e to the x is again e to the x. The derivative of x e to the x is actually a product rule, so here we'll actually get e to the x plus x e to the x. So the determinant of this will have e to the x times that. That will give us e to the 2x plus x e to the 2x minus the other diagonal here, x e to the 2x. So if we go ahead and reduce those terms to 0, then we get our w is e to the 2x. Remember, our w1 is next. That's where we just simply replace the first column with 0 and our right-hand side. So we'll have 0 and e to the x ln x. Our second column for w1 stays the same. So x e to the x and e to the x plus x e to the x. Now when we do this first diagonal, that will multiply and give us 0. Minus, if we go ahead and multiply here, we get a bunch of stuff, right? We get x, we get e to the 2x, e to the x times e to the x, and we also get an ln x, right? So we get, it looks like negative x e to the 2x ln x, lots of stuff. All right, let's go ahead and get our w2 then. So w2, remember that's going to be the Wronskian we get when we replace our second column. So we'll go ahead and leave e to the x and e to the x here. And our 0, e to the x ln x goes in column 2 this time. We'll go ahead and find the determinant. So here, e to the x times e to the x ln x would be e to the 2x ln x. Minus this diagonal, which would be minus 0. So we just get e to the 2x ln x there. All right, so we can probably, I'm going to go ahead and go back and highlight these here. So we can probably figure out, I think, what's kind of happening with these exponentials, right? So remember, our u1 prime is going to be w1 over w. And so in this case, notice the e to the 2x and the e to the 2x there are going to reduce. And so that will just give us negative x ln x. And our u2 prime will have e to the 2x ln x divided by e to the 2x. We'll just get ln of x. And now from here, we'll have to figure out these integrals. So this tells us then that u1 is actually going to be the antiderivative of negative x ln x dx. And u2 is going to equal the antiderivative of ln of x dx. You may already have memorized the antiderivative of ln x, and if you haven't, that's okay. If not, you can certainly do this by parts. If you want to do this by parts, this would be, dv would be dx here if you're going to do this by parts. Let's go ahead and do this one by parts, though. So by parts over here. And we'll say here that u is ln x, and dv is going to be negative x dx. And then that means that du is 1 over x dx. And v is negative 1/2 x squared. We'll go ahead and do these. So we'll get negative 1/2 x squared ln x minus the integral of v du. We have a minus there, so we'll go ahead and make that plus. We'll also bump out the 1/2. X squared divided by x would just be integral x there. dx. If we go ahead and do this, this antiderivative is actually x ln x minus x, technically plus c, but remember we leave off the constant of integration. So this one here is actually then going to be negative 1/2 x squared ln x, and then this just becomes x squared, and we get another over 2, so we get plus 1 over 4 x squared there. We have our y1 and our y2. Remember, our yp is going to be u1 y1 plus u2 y2. Let's go ahead and write all this down then. So our yp is going to be u1, which is negative 1/2 x squared ln x plus 1/4 x squared. You could factor out some things if you want, I suppose. Our y1 was e to the x plus u2 y2, so we have x ln x minus x, and then our y2, remember, was x e to the x. We can go ahead and start writing our general solution now. So we'll have y is equal to yc plus yp, complementary plus particular functions. So remember, we started with c1 e to the x plus c2 x e to the x. And we'll have plus this yp. I'm going to go ahead and distribute my e to the x's so we can see everything that we have. So we have minus 1/2 x squared e to the x ln x plus 1/4 x squared e to the x. Here we have plus, if I distribute my x e to the x in there, we'll get x squared e to the x ln x minus x squared e to the x. Now, just like with our last example, the first thing we want to look for is anything going to be absorbed into this sum multiple of e to the x. If we look through here, we have e to the x in everything, but nothing is just an e to the x term, so we're safe there. If we look for anything that's an x e to the x term, this is not because it has both ln and x squared. This has x squared, this has x squared and ln x also. So none of these actually are going to be combined into the c1 or the c2 terms. We do have some like terms, however, though. So if you'll notice here, I have an x squared e to the x ln x term, and I have another one of those over here. I also have an x squared e to the x term here, and I have one there as well. So we'll need to actually combine those and give the correct coefficient for those terms. So we'll go ahead and say c1 e to the x plus c2 x e to the x. If I have one of these terms and I subtract half over here, then that actually gives me positive 1/2 of that term. So we'll have positive 1/2 x squared e to the x ln x. Here I have negative 1 of the x squared e to the x's plus 1/4 would be negative 3/4, combining those like terms. And our final example here, we have y double prime plus y is equal to tangent x. This is similar to the one that we did in our introductory video, but we had secant x on the right-hand side. So if we go ahead and solve the associated homogeneous y double prime plus y is equal to 0, our characteristic polynomial for the left-hand side will be m squared plus 1. So we'll get m squared plus 1 is equal to 0. That will tell us that m squared is negative 1. Square rooting both sides, we'll get that m is equal to plus or minus I. This is a complex number here. This tells us that alpha is 0 and beta is 1. And that will give us a yc of c1 cosine x plus c2 sine x. So right here we can tell we've got our y1 is cosine x and our y2 is sine x. We'll start doing our determinants. So our first Wronskian here, w, is going to have cosine x and sine x as the first row. Derivative of cosine x is negative sine x. Derivative of sine x is cosine x. If we do our determinant here, that diagonal will actually give us a product of cosine squared x. Minus, here we'll have negative sine squared x, so that would actually make that plus sine squared x. And here we get 1 for this Wronskian due to Pythagorean identity there. For the next one, w1, we'll replace our first column with 0, and our right-hand side of the original, our g of x, remember, was tan x. We'll keep our other column, though. Sine x, cosine x. These are nice. They tell us which column gets replaced, right? So it's easy to remember. Here we get 0 times cosine x, which is 0, minus tan x sine x. Now, let's think about tan x sine x. So that's going to, first of all, it'll be negative. Think of that like negative sine x over cosine x, maybe, times another sine x. So what we'll really actually get then is negative sine squared x over cosine x. Our w2, replacing column 2 with 0 and tan x. And we'll keep our cosine x and sine x column from the original, so cosine x negative sine x there. Here we'll have cosine x times tangent x. And then we'll have minus the other diagonal, which has a 0 in it, so that's just 0. Now this cosine x times tangent x, think about that like cosine x times sine x over cosine x. And then in that case, the cosine x's reduce, and we just get sine of x for our w2. All right, let's use our Wronskians here to get our u1 prime and our u2 prime. So our u1 prime, remember, is going to be w1 over w, and that will just be this fraction here over 1, so that won't change anything. So that'll be negative sine squared x over cosine x. And our u2 prime is going to be w2 over w. Again, over 1 isn't going to change anything here, so we just get sine x for u2 prime. And now we just need to integrate these to get u1 and u2. So u1 is going to be, I'll bump the negative out, so negative integral sine squared x over cosine x dx. And u2 is going to be the integral of sine x dx. This one here I think is not so bad to do. This one we might want to use an identity maybe. So if we think of this as negative integral of 1 minus cosine squared x on the top over cosine x, that might be one way to do it. And then split these up, so think of this as the integral of 1 over cosine x, which would be secant x, and then cosine squared x over cosine x would actually just be cosine x. Go ahead and do that. This antiderivative here is just negative cosine x, right? Remember, we leave off the plus c when we're finding our u1 and our u2. If we go ahead and finish our u1, then the antiderivative of secant x, remember, is going to be ln of secant x plus tan x. So we have our negative out in the front. And then the antiderivative of negative cosine x would be negative sine x. We have a negative out in the front there, so we also get plus sine x, leaving off our plus c. And now remember, our y sub p, our particular function, is u1 y1 plus u2 y2. And so let's write all of that down. So yp is going to be our u1 times y1. So here we have, if I turn this around even, I can put my sine x in the front. So sine x minus ln of secant x plus tan x. That is our u1 times y1, remember, was cosine x, plus u2 y2, so our u2 here we have negative cosine x, times sine x was our y2. And now notice we can do some simplifying here, right? If I distribute the cosine, and I go ahead and multiply here, I get a sine x cosine x that's positive, I get a sine x cosine x term that's negative. So really this is going to all drop off here. We'll just end up with negative cosine x times ln of our secant x plus tan x. And that will be our y sub p. So now we'll go ahead and write our solution, which is our complementary function plus our particular function. Remember, we started with c1 cosine x plus c2 sine x. And then we would have minus cosine x times the natural log of secant x plus tan x. All right, everybody, thanks for watching our examples video for variation of parameters. Hopefully this helped you get some practice. We'll see you in the next video.